back to the second half. So first speaker is Urna. Urna is from Singo Center in Calcutta, and she's going to talk about.
Yeah. Thank you, Sanjib, for the invitation. So I'm going to talk about emergent interaction in active particle systems. So this is based on some works done with my PhD students Ritik and Debraj. So where is the? Yeah. Okay. So I don't need to introduce active matter to this audience. Also, Debashish already provided an excellent introduction. So I'll skip this slide. So what is fascinating about these self-propelled particles is, I mean, one of the points that is fascinating is that they show a lot of novel emergent behavior. So like flocking, swarming, MIPS, motility-induced phase separation. So here are some pictures taken from some experiments. This is motility-induced trapping done by Nitin in ISC here. This is vortex formation. These are dynamic crystal formation. This is an experiment done with some fire ants where they showed motility-induced phase separation. And so what is common in all these collective behavior is these active particles show a tendency to cluster together, irrespective of their underlying interaction. So even if they don't have any attractive interaction, they show a tendency to cluster together. Okay, so one of the important questions is to understand how this effective attraction emerges, and how to particularly understand this from a microscopic picture. So first step is to take two particles and to see whether really one can sort of quantitatively characterize this effective attractive interaction. And already due to the very non-equilibrium nature of these active particles, this is already a challenging task, and there are very few analytical results available. So this is kind of a summary of what has already been done with two particles. So it started with Martin Evans's group, where they looked at random tumble particles on a 1D lattice, and they showed that in the presence of just exclusion interaction, indeed they show an effective attraction. Okay. So there are other works which also showed similar things. For example, Satya and Gregory showed that active particles, two random tumble particles, in the presence of an attractive interaction shows enhanced attraction. Okay. Similar results were obtained for attractive coupling, other kinds of things, and finite tumble duration, etc. So the general consensus is that indeed there is an emergent attraction between active particles irrespective of the underlying coupling. So here what we are going to talk about is something different. So we are going to ask the question whether it's possible for these particles to repel each other. And the answer turns out to be yes, and somewhat counterintuitively, they can actually repel each other when the underlying interaction is attractive and that coupling strength is very large. That's what we are going to talk about. Okay, so this is the outline. I'll first define the model of coupled active Brownian particles, and then I'll talk about harmonic system, which is easy to solve, and then if time permits, I'll go to a multi-particle and short-range interacting system. Okay, so this is the model. So we have n active Brownian particles. So Debashish already introduced active Brownian particles. These are particles which have their own sort of propulsion direction. They have a preferred axis, and that direction diffuses slowly. So here we have n such particles in 2D at an ambient temperature T, and they are coupled with some attractive potential Vr. Okay. So if we look at the motion of the ith particle, so this is the equation of motion. So we are working in the overdamped regime. So we have Ri dot, and this is the force coming, force on the ith particle from all the other particles. So we have, this is gradient of V, the potential, and then there is a thermal noise, and then this is the self-propulsion term. Okay. So Vi is the speed, self-propulsion speed of the ith particle, Ni is its orientation vector, which slowly diffuses with some diffusion coefficient Di. So this is our model, and we will analyze this step by step. So first we have the simplest scenario where there are only two particles. That's the starting step, and the potential is harmonic, so that the equations are linear and we can do something analytically. So this is the explicit equations of motion. So we have the first particle, this is the force on that, this is from the second particle, and self-propulsion and thermal noise, similarly second particle. Okay, and both these orientation angles, theta 1 and theta 2, are their angles with the x-axis, and that diffuse with rotation diffusion coefficients. So since we are interested in the effective interaction, emergent interaction between the two particles, so we decompose their motion in the centroid and relative coordinate. Center undergoes a free motion. We will not talk about it much. It's not so important. But what we will focus on is the relative coordinate. So the distance between the two particles. And we first write an equation for that. Because it's harmonic, so the equations are linear. So this is a very simple equation. So this resembles the motion of one active particle in a trap of strength 2K. There is an effective temperature which is 2T. But there are these active noise terms which are very different from one single active particle. So now I have a difference of two active noises, and as we will show that this actually makes a big difference in the behavior of this coordinate with respect to a single particle in a trap. So this equation, it has three inherent time scales. One is this K inverse, that's the relaxation time scale of this coordinate in the trap. And then the time scales associated to these two active noises D1 and D2. And as it turns out that depending on the relative strengths of these three time scales, we can get three very different behaviors. Okay? So we have this strong coupling regime where this trap strength K is much larger than both the activity time scale, both the activity parameters. So this time scale to relax is much smaller than the active time scales. So that's the strong coupling regime. That's where most interesting things happen. I'll just come to that. And then we have the moderate coupling regime where one of the particles is changing its direction quite fast, and then the weak coupling regime. Okay. Is there a question? No, two dimension. Yeah. So we have a theta, which is the angle with the x-axis. Yeah. So let's first look at this first strong coupling regime. So here K is much larger than D1 and D2. So that K inverse, which is the time scale to relax in the trap, that is much smaller. So by the time these two particles change their orientations appreciably, the R degree has already relaxed. Okay? This is the regime we are working in. And in that case, what we can do is we can assume that the particle is relaxing to a position for fixed theta 1 and theta 2. So we compute that position, and then we average over theta 1 and theta 2 to get the stationary state distribution. So if we do that, so we keep theta 1 and theta 2 fixed, so that the separation vector is given by this form. So N1 and N2 are now fixed vectors. This is the noise coming from the thermal noise, coming from the temperature. And this is a thermal noise, so it's Gaussian. So we can actually compute the distribution exactly. Okay? So let's first take a special case where there is no thermal noise at all. Okay? So then these particles are just deterministically evolving. Theta 1 and theta 2 are fixed. So they go to a particular, a deterministically fixed value of R for a given theta 1 and theta 2 that we can easily calculate. So what is most surprising is that this R, so this is like the stationary state separation between the two particles for a fixed theta 1 and theta 2, that has a minimum bound. So it can, the particles cannot come closer than a particular distance. So this is the distance. So that's like an effective repulsion which is being generated. Okay? So as long as their self-propulsion speeds are different, they cannot come closer than a certain distance. Remember that they are coupled harmonically. So the potential is trying to bring them together to the same point. However, because their self-propulsion speeds are different, an effective push is being generated. So this distance is bounded by a number from below, also from above, but that's not so surprising because active particles in a trap tend to have a maximum displacement bound. So this is a simulation. So these are the two particles with different velocities, different speeds. So if you see that these two particles are never coming within this smaller circle, so they can never come closer than this distance. Okay. So what we see here is somewhat surprising, again just to reiterate this. So we are seeing an emergent repulsion. The particles are not coming closer than a certain distance, and this repulsion is coming purely due to the difference in their self-propulsion speeds. So
keep them fixed.
No, I'm not keeping them fixed. Velocity, the magnitude, speeds, but the direction is now evolving, right? So this is, so what I did is that I calculated this for a fixed theta 1 and theta 2, then I averaged over theta 1 and theta 2, which are uniform, but they have evolved in a much slower time scale. So that's why I am allowed to do this. So this simulation is with, now we have, the direction is evolving, you can see that. Okay. So now it's a real stationary state in the limit where K is much larger than D1 and D2. But we are seeing this effective repulsion. They cannot come closer than a certain distance.
When the velocity they are
No, so aligned is the orientation when they can come closest. So that's like the approach of closest distance, and maximum is when they are anti-aligned. Okay. So basically, one particle is running away, the other is trying to catch up, but because the speeds are different, it cannot catch up. So that's the different distance it must keep. Yes. Yeah.
So is the separation variable?
Mm-hmm.
Separation between the distribution of that equivalent was active dominant particle in a harmonic trap?
No, it's not. I mean, that's what, so it's the structure is similar, so that's the equation. Okay. So this is the separation. There is one term which is like a trap of strength 2K, but the noise is different. Right? Does it answer your question? So if I were to look at a single particle in a trap, I would have only one such term.
Yeah, but there will be effective noise.
Yeah, so that effective noise is what is making this repulsion. That effective noise is exactly what is making, giving rise to this repulsion.
Does the answer depend on the dimension of space?
Answer as to whether there is a repulsion or not.
How much repulsion?
Probably yes. We have not looked at higher dimension, but probably. One dimension, okay, so one dimension, it doesn't, I mean, to talk about active Brownian particles in one dimension doesn't make much sense. If we talk about RTP, so RTP in this limit, it can give rise to only like 4 points, right? So RTP is also not very interesting, but if we go to 2D, ABP and RDP, we expect it to be same because it only depends on the correlation of the noise. Higher dimension, yes, possibly, we expect that the repulsion will still be there, but analytical results will be different. Quantitatively, it will be different. So, yeah. So we have an emergent repulsion due to just the difference of the speeds. So we can go a bit further. We can compute this the distribution of this separation, and it turns out to have such a scaling form. We can compute the scaling function exactly. This is a plot of P of R. I mean R scaled with this R max for different values of coupling strength. And as we see, I mean this weight here is 0, so they cannot really come closer to this. This is done with a finite d, and to the leading order, it doesn't depend on the d. So we can also compute the marginal distribution. That has a more complicated form, but what we see here qualitatively is that this distribution has 2 peaks, which is the signature of the repulsion. So if we look at the projection onto the x-axis, they also have, they are most probable to stay away from each other. So because this is rotationally symmetric, we can also compute the joint distribution. So this again, this hole in the middle, that's
There is a gap on the top side also.
which gap?
The figure.
Uh-huh.
Yeah, that side also.
Yeah, so it cannot also go beyond a certain distance, but that is common. Yeah. Active particles in a trap, they are always bounded in a regime. Okay, so now
It doesn't go to 0, it remains finite there.
the weight, the probability weight, this one, yeah. No. Okay, so yeah, here. So now let's take a special case, V1 equal to V2, and in that case, we were already arguing. So in that case, there is no repulsion. But what we see is what Satya and Gregory saw, that there is an enhanced attraction. So the distribution near the origin, it diverges logarithmically. So if these were passive particles, it would be just Gaussian. Instead of that, we have a heightened probability to be close to each other. So that's like a heightened attraction when the speeds are same. Okay. So next, we ask the question whether this repulsion also survives in the presence of finite temperature, and the answer turns out yes.
Sorry, wait a second. You say that they cannot come close if
V1 is not equal to V2, yes. Yes. There is a repulsion, yeah.
There is a repulsion, but in the previous one you showed.
So this is for V1 equal to V2,
Yeah.
and in that case there is an enhanced attraction, yeah. That is compatible with what we have seen so far. So that's so this here is a larger peak.
The previous case was only with orientation diffusion.
What do you mean only? Yeah, no translational diffusion. Temperature is 0. So now we are going to the case where temperature is finite, and we are asking whether the repulsion survives. So in that case also, because of the Gaussian nature of the noise, we can find the distributions exactly. It looks a bit messy, But what is interesting is that at low temperature, so if you look at this Px versus X plot, there is still 2-peak structure, which is a signature of this repulsion. So at low temperature, it looks like it does survive. So we want to characterize it in a bit more concrete way. So what we
Is there a stick bound or no?
bound on?
Bound on R, no? And it cannot come closer than something.
So yeah, I'm coming to that point. Yeah. So that strict bound is true for t equal to 0. But now when we have finite t, we cannot have any lower bound, also upper bound once we have a temperature. But what we see here, so what we try to do is to define an effective temperature, effective potential. So had these been passive particles, we would expect the separation distribution to be of this form. Two passive particles coupled by some potential V would have this form. So what we do now, we say that, okay, suppose, we say that there is an effective potential, and we extract that potential from the distribution. Okay, there is a ambient temperature T, and then we look at this effective potential to see whether we can see some signature of this repulsion, and it turns out that yes. So we extract this effective potential from this exact solution here, PR we know. So we extract this potential, and it turns out that at low temperature, indeed this potential has a minimum, which is at some positive R. So the underlying potential was harmonic. So this dashed line, this is the underlying potential we had. So that had a minimum at R equal to 0. Now with this V1 not equal to V2, this potential has a minimum which is at a finite R. So that's again a signature of repulsion. There is a peak, yeah, in the probability distribution, which is, okay, if we look at R, there is always a peak which is at R not equal to 0, but this is what is saying that there is indeed a repulsion. Okay, and if we increase the temperature, the thermal noise kind of takes over, and this effective potential approaches the underlying one. Yes. Temperature of the bath.
You don't attempt to define an effective temperature.
Finite?
You didn't try to define an effective.
So in this strongly active regime, it's not, we cannot define an effective temperature, but I'll come to the next regime where we can. Okay, so here now I'm just trying to convince you that, okay, even even when you have a finite temperature, up to a certain temperature, this repulsion survives. This is not a purely T equal to 0 effect. Okay. So if we look at this T star, beyond which the repulsion disappears, so this is a plot of T star versus K, so it goes down as we increase the coupling strength. So there exists a T star, and again just to say that for V1 equal to V2, there is no repulsion even for finite temperature. So, okay. So far we have looked at the strong coupling regime. So K is much larger than D1 and D2. Now we come to another regime where it's moderate coupling. So K is still larger than the rotational diffusion constant of one of the particles, but the other one rotates kind of fast. Okay? And in that case, if we look at the equation of the separation, then it really resembles one active particle in a trap. So we only have one active noise. The N2, it rotates so fast that it has, we can actually describe it with an effective temperature. So this T effective is the ambient temperature plus this thing, the effective diffusion coefficient. Okay. And so this problem was solved by Abhishek and Anupam and co-workers in 2020. So we translated their result to this case. And once again, we can define an effective potential from this PR. And it turns out that here also the minimum of the effective potential is not at R equal to 0. So there is again an effective repulsion in this case also. But in this case, the reason is something different. This is like a single active particle, and it has this tendency, when it's active, it has this tendency to stay away from the minimum of the potential. So the strongly coupled regime and the moderately coupled regime, those are physically different. In one case, the difference, the repulsion was coming purely due to the difference in their propulsion speeds. In this case, it's more like one active particle in a trap. Okay, so the third case is weak coupling regime, where we have, both the particles behave like passive ones, and we expect the whole system to behave like two passive particles with some effective temperature, which is this. And it turns out that indeed it's true. If we look at the R distribution, this is like that. Okay, so let me summarize what I have said so far before going to the next part. So we have looked at emergent interaction between harmonically coupled active particles, just two particles, and we can characterize this by some effective potentials. And it turns out that when they are very strongly coupled attractively, then there is an effective repulsion emerging purely due to the difference in their speeds. And so this is kind of a generic feature. I mean, although we used active Brownian particles, we expect that other particles like run and tumble or direction reversing active particles, they would also have the same behavior. Not active Ornstein-Uhlenbeck, because there the speed is not fixed, the speed is varying. But this kind of particles where the self propulsion happens with this fixed speed, we expect this kind of thing to emerge. So the next question, yes, yes. Mm-hmm. 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 No, so it will have, I mean, we basically assume that had these been passive particles, what would the effective potential be, right? So if we actually take two passive particles and perform a simulation with the same effective potential, we expect the same distribution. No, but I mean, that's the way we defined it, right? Just two particles, thermal noise at some temperature coupled by a particular potential. So we expect this to go to equilibrium with this e to the power minus beta VR distribution. That's the way we define the effective potential. Okay. Yeah. Mm-hmm. Mm-hmm. Yeah. So there will be, I mean, various signatures which will be very different. Only at the distribution level, so 2-point correlations will be different. Only at the single point distribution level, these will be same. But there will be other signatures which, I mean, in this case, we have other signatures of activity.
It's not completely clear to me that the effective potential will be independent of temperature when you define it. Why is it that it's always e to the power minus 1?
So, no, it's not. I mean, it can be. But for a fixed t, if we keep the t fixed and then do this, then yeah, you're saying.
You said it will not happen for AOUP, but AOUP, if you take for the two particles with two different velocity.
But AOUP doesn't have fixed velocity, no, because two distributions,
I mean,
very narrow.
No, in the sense that this time scale for AOUP, you could take for these two AOUP, two different time scales. I mean, different divided to the minus
So,
by tau 1 and
tau 2. Two time scale. So here also we have two different time scales. I mean, so if we have V1 equal to V2 and different time scales, that doesn't give us repulsion. So I'm not very sure. Yeah. I think we need. Yeah. Gaussian. Yeah. AOUP is purely Gaussian. Yeah. Some sort of two peak with the kind of narrow peaks. So the next question is how robust is this emergent repulsion? So we have seen for two particles and harmonic coupling. So the first question is whether we can have it for non-harmonic coupling. Answer turns out to be yes, as long as it's a long-range attractive potential with forces, where the force is increasing with r. So that also we can show. And multi-particle case, yes. And then the final question is whether we can also see this for a short-range interaction. And the answer also turns out to be yes, but then we need, many particles. So in the remaining 10 minutes, 15 minutes, okay, I will just describe briefly. So we have, now we consider again n active Brownian particles, but now they are not coupled by, long-range harmonic, but we have just a truncated harmonic potential. So there is a finite range of interaction. We put so that the system is reaching a stationary state, we put the whole system in a box of size which is much larger than the interaction range. And so particles within a distance are not, they see each other. If they are outside this distance, they don't see. So again, to take the simplest case, we take n1 particles with speed v1 and n2 particles with speed v2. Now we want to see what happens. Okay, so it turns out that in this case, we can have three different regimes. One is the disordered regime, where the interaction range is very small, so all the particles are diffusing randomly. And then if we increase the range of interaction a bit more, then we see the emergence of a phase where the slower particles, so particles with smaller speed, they sort of self-assemble into a ring. All the particles are forming a ring, and the faster particles just diffuse around randomly. So this we are calling a partially ordered phase. So there is a spatial ordering, particles are forming a ring, and there is also an orientational ordering in the sense that the self-propulsion directions of all the particles are pointing radially outward of this ring. Yeah.
The interaction potential is a Gaussian truncated,
Harmonic truncated, yes, yeah. That's the simplest case because I mean when they interact it's linear, so we can actually solve. Yeah. So that's the first case we did.
So the radius of this ring depends on this R0. I mean, how does it?
Yes. So the radius is so we have. I'll come to that. I'll come to the radius.
So that's the point particles, right?
Point particles, yeah. Point particles. So point particles, but they can see. I mean, they interact. They feel the force of attraction from other particles within a radius r0. Yes.
So if you form rings, why not a cluster?
Okay. So this ring you can show easily. So if you just take, I mean, just a collection of ABP particles with no short range, nothing, then also and coupled harmonically, you can show that they actually form a ring. Okay. So basically, this is to balance. So the ring is coming from the balance of these active forces. So you have self propulsion. So the particles opposite, diametrically opposite each other, they sort of cancel this force. So this ring is the configuration which comes from force balancing the harmonic force and active force.
So that is
Okay.
a collection of pairs in practice.
Not exactly pairs, but because I mean the force on each particle, it's cancelled by all the other forces. It's like as Deepak mentioned once, it's an electrostatic force cancellation scheme. No. So several rings form while I mean it's a transient state, but eventually it will just form one ring because it's a finite box. So they will once in a while come close to each other and then they will.
Because with the flocks of birds,
Mhm.
sometimes you have one big one, but sometimes they all separate.
Yeah, but
and you're mostly dependent in the flocks until they meet them again.
So here also, I mean, if we have infinite space, so here we are talking about stationary state, right? And the stationary state is unique, and that's just one ring. So this is because it's a finite box. So eventually, it will. I mean, if we have two rings, eventually it would come close to each other, and then they emerge. So we have seen this in the transient phase in the.
Number of particles,
Yeah.
the ring radius will depend on the velocity.
It will, yeah. So the ring radius is essentially V1 by Kn1 in at least, I mean, deep inside one phase. Okay. So no, at least, yeah, it doesn't. Yes. The persistence is high. Yes. So we are in the regime of strong coupling, which means that the D1, D2 are very small. So persistence is high. Yes. The box is finite, but much larger compared to R0. Mm-hmm. Possibly, but we wanted to avoid that because we want to see. So first of all, we want to understand these phases. We want to calculate the order parameter, etc., if we can. And so we wanted to have, I mean, we wanted to be in a regime where things are unique and nice and simple. So that would be the next step, to see whether one can really have a metastable state where various rings actually survive. But I expect it will be, I mean, maybe even exponential L or something. So now if we increase the range of the interaction even further, so we have such a phase where both species organize into two concentric rings. Okay, so there is a little difference in the formation of this first ring and second ring. So this is really discontinuous. So when we go from disordered state to one ring, the whole ring forms at one go. I mean, but here we can have a regime where some faster particles are in the ring, but the other particles are still diffusive, and eventually they form these two rings. So we have these two different ordered phases. We are calling it partially ordered and completely ordered or fully ordered. And the ordering is of two kinds. One is spatial, formation of the structure, spatial structure, circle, and the other one is orientational. So that so if you see here, all the particles, there these little arrows are their self-propulsion, I mean the orientation vectors, and they are always pointing out radially from the center of mass. So So it turns out that, okay, before that. So how to characterize this order? So we sort of define two different order parameters. One is the radius of curvature of each ring. So we have one phase where it's completely disordered, so that I mean this thing is, I mean the radius is like infinity, so order parameter is 0. And then two other phases. In one case we have one R1 is finite, so K1 will be non-zero, and the other phase fully ordered, there both of them will have finite value. And then also to estimate the orientation order, we measure the I mean just the dot product of this vector with the corresponding nj, and that is the orientation order parameter. Okay. And so for this harmonic case, it turns out that Debraj could calculate the phase boundaries exactly by just looking at static assemblies and force balance. And so it depends on, so we could, I mean our phase space is characterized by three parameters: mu, the ratio of n1 and n2, the two particle species numbers, and then phi 1, which is self-propulsion velocity of that species, divided by k r naught n1. So v1 by kn1 is one length scale, as we saw in the previous case. So v1 minus v2 by kn, that's the length scale of the repulsion, and r naught. So the ratio of this radius and r naught, that's one parameter, and then similarly phi 2. So we have this phi 1, phi 2 plane for a fixed mu, and this is for mu equal to 1. This is the phase diagram. This is the regime where two rings are forming. So psi is my, I mean coming from this order parameter, psi is defined as psi 1 plus psi 2. So here psi is equal to 2, which means that both rings are formed and their orientational ordering is complete. So this is the two ring fully ordered phase, and these two are partially ordered phase. Slower particles have formed a ring, faster particles are still roaming around, and this is the disordered phase. Okay. And if we look at the full 3D space, so phi 1, phi 2, mu, this is these are the phase boundaries. Okay, it's maybe a bit harder to see. So we know the boundaries exactly in terms of some functions, and we have to solve the transcendental equations to find it numerically. We don't have explicit expressions, but just in terms of solutions of some transcendental equation. So this again here is the disordered phase, and that side here is fully ordered, and here is the partially ordered phase. So we have the full phase diagram in 3D plane. And which boundaries? No, not straight line at all. Yeah. So here these straight lines are only for mu equal to 1, because we have n1 equal to n2. But this I mean along mu direction, this is very non-trivial. So these are the line. So this is one line here, which is not a straight line. Okay. And this little line here, so this we know the phase boundary, but we don't know the order parameter there exactly. Okay, so we also went a bit further ahead and wanted to check whether again this whole structure is because of the linearity of the equation or not. So we also performed numerical simulation with Lennard-Jones potential, and it turns out that qualitatively the behavior remains same. I mean truncated Lennard-Jones, we have a finite range on that, but the qualitative behavior remains very similar. Okay. So I'll just conclude. So what we have seen here is we have investigated role of speed dispersion in active motion. And if we look at like few particle cases, it turns out that because of the speed difference, there is, I mean particles can feel repulsion, which is kind of a novel phenomenon, because active particles are always thought to have effective attractive interactions, giving rise to these MIPS and other kinds of ordering, clustering, etc. And now if we have many particles interacting with even a short range interaction, we see that this kind of ordering transitions happening. And we are still working on that, trying to characterize these different phases and see, I mean, the exact order parameters, etc. And one question remains is that there is a recent work where they showed that if you have particles with speed dispersion, speeds drawn from a distribution, it can actually oppose cluster formation. So they have shown that this kind of dispersion hinders formation of MIPS. So we would also like to see whether with these simple models we can sort of emulate that. So yeah, I'd like to thank Ritik, Debraj and Shreya, who is a PhD student now in Germany, for these works, and also SCRB. So questions? So truncated harmonic potential is important as far as analytic solutions are concerned, because then we can do the force balance and find the phase boundaries, but qualitatively no. So we also did with Leonard Jones.
You do see a strong density fluctuation on the ring.
Strong?
You do see a strong density fluctuation on the ring.
We don't see a, okay, this we have also characterized that. So that is more or less Gaussian. So if we look at the distribution of R1, that is Gaussian just from, just central limit. Okay.
First,
So in the two-particle case, cannot understand some simple argument. So they cannot come together beyond certain points. So means that they are actually cannot be aligned.
No, they can be aligned. So what happens is
they can penetrate.
no, because because the speeds are different. So actually they come closest when they are parallel. Okay. So basically, so two particles are moving in parallel direction. So if they are anti-aligned, then of course they are farther away. But when they are parallel, so because the speeds are different, one is moving at a faster speed, the other one cannot cope up. That's where the minimum separation is coming from.
No, but why there is that bound is there? It cannot.
Because the speeds are different.
Maybe.
Because the no. So mathematically, it's kind of easy to see. So if you look at this,
But physically, I don't
physically,
know.
because
Physically, it's just a dramatic result. I don't know.
no, one particle is moving faster, the other cannot catch up.
That's okay.
Yeah.
But from behind.
From behind, yeah.
No, but the high velocity particle coming from behind.
yeah, then
So
you
then,
can
I suppose meet, no, some point.
No, but it's not 1D. So
It's not 1D,
yeah,
but
it's not.
That's the main
No,
point.
I
It's
understand.
not 1D.
It's
Yeah.
not 1D, but
Yeah.
it means that there's some anti-correlation. They just deflect or something.
No, so
At a certain point.
no, because no, there is no deflection. So if you look at
No, larger velocity particle
this thing
coming
here.
from behind. What stops it to come beyond that?
no, so there is no behind, right? In the sense that it's
No,
completely.
I consider a situation behind. Sorry. Maybe we discuss.
So if you see here, you can just see that this is the region. So they are moving.
Anti-correlation. So that's what I'm saying. They are
Anti-correlation in.
means they are never, parallel sort of thing.
So-
they cannot come from behind. There is some deflection.
No, so you see here, so the maximum distance is when they are trying to move away, but the potential is holding it, and the minimum distance is okay, that's the best I can do. So here you see that's the closest they could come when they are kind of parallel.
No, they are not parallel.
So when it becomes parallel, it will come on that.
You're cutting down time from your own talk.
During the merging process, is it somewhat similar like the coarsening of phase separation?
Merging in the ring.
Of two rings, yeah.
So that we have not studied at all. It could very well be. We could not. We have not done anything in the dynamic regime at all.
I did not get one point. If you look on the next slide or the next after the next, again, here.
Here?
Because this result which you showed in the boxed on top, it's quite a well-known result for the generalized Ornstein-Uhlenbeck in presence of dichotomous noise.
Okay, I don't know that result, but this is also.
But I do not see where from the dichotomous noise comes. And this is exact result for some strength of the potential and nu1 equal to nu2.
Yes, but this is again.
Otherwise, you may get a different power, not necessarily one half. You may even inverse the shape. If you
can inverse the shape. Yeah. So when you change the relative time scales, you can inverse the shape. Yeah.
Not the time scales, the strength of the potential. If you lose it
Also,
a little
yes.
bit,
Because it depends
you
on
may
the.
make it like this.
So this is also, quite common for active particles. So of course, I'm focusing on the active regime.
But this is exact result for Ornstein-Uhlenbeck driven by dichotomous noise, and I don't see where from dichotomous noise
No,
comes.
because so this result, this part here, this is coming at the. If you look at 1D, right, the marginal distribution.
Yeah.
And this is so. If you look at the projection, this is again basically either moving with V0 and minus V0, right, with
plus
some
minus
correction.
1.
Yeah.
Oh, okay.
Between plus and minus 1. So it's not exactly dichotomous, but it's bounded.
Okay.
So the boundedness of the noise is what is giving this.
Okay.
Yes, Urna, have you considered two particles, but if you make their coupling not reciprocal?
Okay, that's of course a very interesting
Next project
question.
together,
Yeah.
very good.
Yes.
So you had a picture in which you form rings, and they keep on drifting. Is there any statement about how the drift velocity depends on the size of the ring?
Drift velocity depending on the size on the ring of the
Number
ring.
of particles.
Yes, there is, but I forgot now. Because so basically, it is coming from the center of mass motion, okay, and the center of mass motion is pure diffusion, but it depends on the cancellation of the forces, right? So this, I mean, it becomes. I forgot the exact scaling, but it becomes completely independent of n in the n going to infinity limit. Because then.
Why does the ring doesn't rotate?
No, because there is no ring rotating. So basically, if you see this thing, what happens is that. So the moment this orientation changes, they also shift along the ring. So that doesn't allow it to rotate in any direction. Yeah. So it's always radial, and the moment it rotates, it's also position shifts on the ring.
Okay, so let's thank Urna again. Next speaker is Urna from Center, Calcutta.